for having me on the show. I appreciate that. So the 1430Q project is a multifamily residential. It's a mixed use that's constructed using 6 levels of wood frame construction on top of 2 levels of a concrete podium and a basement. So even though I didn't know it at the time that we were working on the project, but this ended up being the first 6 over 2 level podium project in the US. So that was kind of cool to be able to work on a first of its kind. So,
Absolutely. And is light frame project, so that's a 6-story stick frame. So here it's, for anyone listening right now, it's like we do in Australia with your 1 or 2 story residential construction just with studs, but scaled up to a taller type building. Is this type of construction common for 3, 4, 5 stories where you are?
yeah, it is very common. You know, wood seems to be the most efficient, kind of predominant material to use for that short to mid-rise building height. It's, you know, we've got a lot of contractors that are familiar with the material, and it's always going to come out cheaper than concrete or steel, certainly in this area. So.
And why was it used for the 6 stories in this case? So I understand this was pushing the boundaries. So 5 stories might be common, but 6 stories is of light frame is a bit bigger than usual from where you are.
Right. Yeah, there was this project also, you know, wanted to try to keep with the wood frame because of its familiarity. The owner was going to be able to get better bid from contractors to get a good competitive pricing on it. This project, being that it went taller than the code limited 5 stories, we had to go through an AMMR, an alternate means and methods request process to be able to allow that to happen. But I think, you know, we still wanted to try to keep wood as the main system for the residential because it was known to be a cost-effective solution.
Mm. And one of the challenges I'd imagine at this height is the stability system. So can you tell us about the stability system you designed all the way from the top of the building down to the foundations and how it transfers lateral loads? I understand is earthquake one of the big factors where you are, I'd imagine, as well?
It is, yeah. In Sacramento, the earthquake level is moderate, but we are very close to high seismic regions like San Francisco. So we do, you know, when there's a big earthquake in the San Francisco area, it can certainly reach out to Sacramento and cause some effects. So that is our primary lateral design constraint. With the wood building up above, we wanted to keep it with wood shear walls, and there's a code limitation that would limit the height of wood shear walls to 65 feet. But as we increased this building by 1 floor, that 65 foot was exceeded as well. So what we decided to do there was we had 2 options. The first would have been to go through some laboratory testing to try to justify the taller wood shear wall system and look at the deflections and make sure all of that was going to be you know, what we were looking for. The second option, and the one that we ended up going with, was to simply extend the concrete podium level seismic system up by 1 more floor. So what we have in a general sense now is we have 5 stories of wood shear wall on top of 3 stories of concrete shear wall.
Yeah, and I actually looked at you did a webinar as well, which I found really interesting. And there's less shear walls than there is timber shear walls. So was it quite kind of interesting trying to transfer the load from 1 floor back down from the timber to the concrete?
Yeah, it was interesting. So I guess the key focus point of where all this happened is at level 4. So the 3rd floor would be the first level that residential layout started. So we had our usual wood shear wall layout coming from the roof down through all the residentials. when you get to level 3, instead of having a wood shear wall there, we simply replaced it with a concrete shear wall. Now, the other tricky aspect about it too is that the wood shear wall systems are a double party wall. So there's 2 walls side by side with about a 2-inch gap in between them. And so when we get to level 3, rather than doing 2 concrete shear walls side by side, we elected to go with just 1 concrete shear wall and then put another wood wall next to it. And this was just a little bit of, better economy to not have 2 concrete shear walls right in the same vicinity when one was, more than enough to handle the loads that we had. So the load transfer from the double wood shear walls above, it comes down, it hits the diaphragm at level 4, and then all of it transfers over to this single concrete shear wall. Mm-hmm. And then that load comes down further to the concrete podium at level 3.
And what contributes to the stiffness of the wood shear wall at level 4 in this case, I think, where it's got the most lateral loads? How thick is the bracing on it, and is that contributing the most, or the connections from the bracing back into the frame? So how does this is probably an elementary question for you in the US, but it's something that's we're still working out here in Australia about what limits we go to for, the thickness of sheeting and things like that.
Okay. Yeah. I think if I understand your question right, the wood shear walls up above being that they were the party walls, they're actually rather long because they were running the full length of the unit. So we had some walls that are 35, 45 feet long. The shear wall sheathing is a standard 1/2-inch plywood or OSB as it may be. And so that's the stiffness of that setup is pretty comparable to what you'd see in a normal 5/1 type of building, any 5-story wood shear wall. As you get into the concrete level, level 3, which had the concrete shear wall in it, since we simply replaced the wood wall, it's still 45 feet long, and now it's concrete, so it's got way more stiffness than the wood shear wall portion would have. And part of that stiffness difference is what also allowed us to do a 2-stage analysis where the upper wood portion of the building is considered separately as a kind of a standalone structure, and then all of those base reactions of that wood building are imparted onto the concrete structure below it.
Great. And in some places where there's openings on the webinar, I saw how you, in places of concentrated load, you laminate studs together. How many studs do you laminate together where there's concentrated load? And is there any limitation on how many you can put together before it just starts becoming a bit silly? Okay.
Yeah, I think what you might have been keying in on there was our hold down systems, our overturning restraint. And that would be the compression posts that we use for the compression side of the shear wall. And the hold down system is basically just a continuous steel rod that runs from the foundation, if you will, so level 3, all the way up through the roof. That takes the tension component. And then when the earthquake changes directions, it's got the compression side, and that's what these studs are. So they're just stacked up right next to each other, and it becomes quite a large, very long element. Is there any practical limitation to that? Yeah, maybe. We kind of got to that point here where it seemed like it was getting a little bit silly. The compression studs there was a lot of them, that's for sure. But I suppose, as long as all the engineering is working out to consider the center line of action and all of those kind of things, then it should be working out okay.
Fantastic. So we've got 6 stories of timber frame landing on a concrete transfer structure. What kind of system did you use for the transfer structure at the first concrete level?
Mm-hmm. Yeah, the level 3 was our true podium. That would be the, I guess the term podium comes from where the 3-hour fire separation occurs at. So that's our really thick concrete slab. And the wood levels come down, they stack on that single level of concrete wall, and then that concrete wall sits on the podium at level 3. Now, because we had parking in the level below that, the shear walls of the residential layout didn't line up with the shear walls down in the parking level, and so we have a discontinuity within the concrete system there. And we resolved that by having some beam elements that were very wide, flat, wide and shallow beams within the concrete slab that was able to resist the overturning of the residential shear walls above it. And actually, we had another level of discontinuity too when you got down to level, the ground level, because at the ground level, then we had, again, parking in the basement, which had a different layout. And so some of the shear walls didn't line up there either.
Gotcha. And another really important aspect of design is the vertical movement within the building. How much movement did you design for per level? And how did you incorporate, or what did you look at to, I guess, mitigate any risk of structural damage to the building because of any kind of movement?
Okay, yeah, the vertical movement, the shrinkage of the wood members certainly is a little bit more, since we've got an added level of wood in the system. I think the number that we came up with was about 1 3/4 inches at the maximum amount. And so I don't recall what it was on a floor by floor basis. But I'd say, we did use a semi-balloon frame technique where the walls have their top plates right up to the underside of the sheathing. And as opposed to a normal platform construction, which would have another plate in there, which would have more room for shrinkage. But other than that, we specify moisture content less than 19% to try to reduce how much it's going to shrink. And then, at that point, it's letting the architects and the MEP designers know about what our estimated shrinkages are so that they can accommodate that in their own systems, like flexible couplings and joints and wall finishes and that sort of thing.
Do those flexible couplings and wall finishes, does that add much cost to the project? These other elements that I guess are pretty novel if they were used in Australia.
Yeah, I guess I didn't have a good handle on what the cost was for those types of items. If I were to guess, I'd say they probably didn't add too much cost. It would have been, similar in the ballpark of what you would expect for a normal 5/1 podium type of project.
So shrinkage is obviously, excuse me, shrinkage is obviously one big element of vertical movement, but there's also your compressive element, compressive strain within the building. And listeners may know that when we put load path through perpendicular grain, then there's going to be a lot more movement than it's going through parallel grain. So is there any other design criteria you have as you got the building to minimize perpendicular grain? I mean, do you entertain the idea of balloon framing or anything like that? Okay.
No, I think, as far as I'm aware, I don't think we consider balloon framing here. That certainly would help to reduce some of that cross-grain compression, but yeah, I guess at the beginning stages, I think we knew we just wanted to go in with the semi-balloon and have it be, as much of a platform frame as they could for simple construction.
So we're using light frame walls, and what did you use for the floor system?
Yeah, the floor system was made of 2x material in gang nail trusses. So they were I think they were 11 7/8 inch deep trusses. And then the corridor joists were standard 2x8s because they were spanning the short direction.
Great. And you obviously did a lot of innovation here outside the standard of what goes normal and in the code. Was there any resistance from a fire point of view, or any extra detailing or design implications from looking at the fire design and safety of the building.
Mhm. Yeah, the fire design was, I'd say, the primary focus of the alternate means request that allowed this building to go taller. So the developer and the architect worked closely with Woodworks, actually, here in the States, which I think is probably your contemporary.
Mm.
And Woodworks helped to commission this fire engineering study that was done by a third-party engineer. And they determined that we could increase the level of fire protection of basically the whole wood building. So we made all of the walls, all the floor systems, everything was a 2-hour rating. And then in addition to that, we had a couple of spots within the wood building where we added a 3-hour fire separation wall. So that would, from a fire standpoint, would kind of effectively separate two halves of the building. And we added an extra stair access to the roof, and some other, fire protection features, electronic type features that I'm not totally familiar with. But yeah, so that was all the things that this engineering report recommended in the alternate means request that allowed us to go forward. And I'd say, the building department seemed pretty on board with it. They seemed to be happy with the analysis, and they even went as far as to say that this building was, better than a Type 3A, and even approaches a Type 2B in terms of fire resistance.
Mm. And were the sprinklers utilized for the building as well?
Yes, yeah, we did have sprinklers throughout.
Yep. And then you've just got plasterboard, I'd imagine, on top of your frame to get the 2-hour fire rating. Is that right?
Yeah, it ended up being in some cases 3 layers of gypsum board on the joist, the floor joist.
Mm. Wow, 3 layers. And is there any? I think in Australia there's been a few questions around the connections of the plasterboard into the frame. Is there anything around that you need to keep in mind?
Yeah, one of the biggest things, at least in this jurisdiction, is how the floor intersects with the wall. And they've always wanted to have the wall fire resistance be continuous basically from sheathing to sheathing. So they want to see that gypsum board be continuous all the way up to the underside of the sheathing. So that means that our floor joists can't penetrate through that. But instead, what we're able to use is there's a proprietary hanger, a joist hanger that is basically a top flange hanger. So it'll sit on top of the wall, but it has the ability to kind of reach out over the gyp board to support the joist without the joist needing to penetrate through the wall system.
Mm. And then I'd imagine with the wall system as well, if you got plasterboard there and you're accommodating for movement, but we don't want cracking in the plasterboard on the wall, do you nominate a gap, say toward the bottom, to allow for the studs to move up and down?
Yeah, it's a good point. I would say we didn't specifically detail that. I think the gyp contractors probably do that already. I've seen that before, where they'll put a gap at the bottom of the gyp. But it's not something that we would usually detail on our structural drawings.
Yeah, fantastic. Well, as we come into the end now, really appreciate your time, Ryan. What do you see as the future going forward with timber construction? It's obviously been an interesting year. Do you think there's an exciting future? I understand you're really interested in sustainability as well. Is the trend towards timber similar where you are?
Yeah, I think it does. Certainly this project being a first and now setting a precedent is. We've had a lot of interest in this type of building elsewhere, and even had some questions on, hey, could we do this? Could we go 2 more levels above the podium with concrete walls and then allow the wood to go up after that? So that would still allow you to use wood for the majority of your systems, with still keeping the shear wall aspects within a code limitation. So, and mass timber too is definitely up and coming. We're seeing a lot of interest in that around here. Finally, I'm very happy about that. I'm looking forward to that. But yeah, wood is, I think, clearly the sustainable choice for its ability to sequester carbon. And also just the fact that it's lighter weight. A lighter weight building allows you to have smaller foundations and a lighter seismic system. So, wood's definitely a good choice.
Yeah. And I saw in your bio you're the co-chair of the Sustainable Design Committee. And being an engineer, I think a lot of people are cottoning on to the fact that operational energy, it's going down at a fast rate, meaning the impact of materials is just increasing more and more. Do you think engineers are going to have a big role in reducing the greenhouse gas emissions that we emit from the construction of buildings?
Yeah, I think we do. There's an initiative here in the States, at least it's called the SE 2050 Challenge. And it's really trying to bring awareness to structural engineers that we really do have a part to play in reducing that embodied carbon. And the choices that we make can greatly affect that number. I think it's around 40% of the embodied carbon in this industry is from the building itself. So it's there's definitely some gains to be had there.
Yeah, there's a lot of room for innovation. Well, thanks so much for coming on the podcast today, Ryan. If people want to find out more about yourself or your company, where should they go?
Sure. Yeah, I guess our website, our company name is Buehler, and that's Buehler. And our website is buehlerengineering.com.
Thanks so much, Ryan.
All right, great. Thanks very much.